Yeah, everyone. Master Mind here again. So, in today's class, we're talking about physics and it's a very, very sweet and might be taxing topic, but we'll make it simple. Periodic motion. We're focusing on simple harmonic motion. Anyways, I'll just start. What is periodic motion? Well, to keep things simple, to keep things very, very plain. Periodic motion is a motion that goes through and through, as moves up and down. Sometimes we might call this oscillatory motion. Now, a very common example of simple harmonic motion, periodic motion is simple harmonic motion. So if you want to define the simple harmonic motion, the simple harmonic motion is a motion of an object that moves in a periodic manner. You can say the motion of an object that moves in an oscillatory manner, any harmonics. Now, there are two systems that has, or there are two systems of simple harmonic motion, let me like it. And these two systems we have the mass spring system, and the next one is the motion of a simple pendulum. Now, here in this video, we just focus on some important terms, and this is just an introduction to cellular motion. Some important terms in the mass spring system. So, alright, so this is a diagram of the mass spring system. Let me just quickly explain what we have here. We have the hinge where we hang, just like a wall or like a support where the spring is hanged. And then this is the spring, and this is the mass that is attached to the spring. And this dotted line you see, or this shaded dotted line you see here, shows where the equilibrium point, where the mass will down, then we stop, that comes to rest at this point. Now, what is the product here? Just imagine this. Imagine I use my hand to hold this mass, and I pull this mass with the force, I pull it down away from the force that moves it away from the equilibrium point. Now, the distance with which I pull this mass from, let's call it x. Let's call it x. That distance x. And this mass was pulled with a particular force, let's call it the applied force. Now, if you can imagine this thing, well, if you are holding the mass, you feel like a pressure that will pull this mass back to where it's coming from. That pressure that wants to pull it back, or that force that wants to pull it back, is called the restoring force. And that restoring force is always opposite direction to the applied force. That's it wants to go back, it wants to pull the mass back to its original position. So let's call that force restoring force. FR, which is restoring force. So I'll write it here. FA means the applied force, and FR means the restoring force, which is always opposite direction to the applied force. Now, there's a law that describes the relationship between this restoring force and this distance, or this distorting distance, let's just say that law is now Fuchs law, which is commonly stated as provided the elastic limit of this spring is not exceeded, the distorting force, or which is called the applied force, that force that pull the mass away from the equilibrium position, is directly proportional to the displacement, or what we call extension. So the next thing we have to do is Fuchs law and how it applies to the mass spring system. So which says that the restoring force is directly proportional to the extension. So are you set?
Yes.
Have you been videoing me?
Continue. I've got it, don't worry.
Alright. Well, Fuchs law, which in the simplest form, it says that the restoring force is directly proportional to extension. Alright. But in this video, I will be using extension here as x, which is displacement. So I will say that the restoring force is directly proportional to x. Here, x here is the displacement. Now, mind you, x here is not maximum displacement. Now, x here is just the distance from the equilibrium position of the mass to a particular point. that is not the equilibrium position. And that point that we are going to is not the maximum displacement, because the maximum displacement of the mass spring system has another term, which is called amplitude. I am talking about that. Now, in science, once we remove the sign of proportionality, we put equal to and constant. And I wonder why I didn't put negative sign in the restoring force. Well, one thing is that force is a vector that you can take, and negative sign there shows the direction of the vector, it's opposite to the direction of the applied force. But in Hooke's law, we are dealing with the magnitude of the force, and magnitude is scalar quantity, and scalar quantities are always positive. Please notice that scalar quantities are always positive. So this is another video of mine talking about vectors and scalar later on. Now to remove this, we put equal to a constant. So the restoring force is going to be equal to spring constant times x. Where k here is the spring constant of the spring. That's, it's lost provided the elastic limit is not exceeded. That's the elasticity, the elastic capability of the spring is not exceeded. Now x here means displacement, like I've written before, and FR here means the force, or you can call it the distorting force. Now, if you want to make K the solid of formula here, the spring constant is going to be equal to the restoring force over x. So it means that the restoring force over x is a constant. And when you have something as a constant, it means that there will be an initial value and there will be a final value. So you can generate another formula. By the way, please note this as a formula for the simplified form of Hooke's law. You can generate another formula that says that, I'll write it up here, that the initial restoring force over the initial displacement is equal to the final restoring force over the final displacement, where FR1 means initial restoring force and FR2 means final restoring force, and X1 here means initial displacement. X1 here means the initial displacement, and X2 here means the final displacement. So that's about the basic idea. This I have is start that the important formulas I'm going to put inside brackets, inside the big block, sorry. And that's the one I want to take note for possible upcoming exams or semester tests. So that's about it for the basic idea of Hooke's law concerning mass spring system. So we have three systems of mass spring here, and what are these diagrams all about? I want to tell you what happens to potential energy, kinetic energy, and mechanical energy of mass spring system has three cases for compression, equilibrium, and expansion. Now just review on something real quick. As long as friction is absent, the mechanical energy of the mass spring system is potential energy plus kinetic energy. Please, I would say as long as friction is absent, as there is no friction in the system, the mechanical energy of the mass spring system is equal to potential energy plus kinetic energy. Now, all I want to do here is what happens to these three energies in these three system of mass of these three mass spring systems. So I will do two, and I will ask the audience what they think or what they feel the last one will be. So let's come to compression. Now, let's work with it. Now, imagine this is your hand, and you pull the mass. This is the equilibrium position. You pull the mass up as you compress the spring with the mass. Now, the mass is in your hand. Now, you are pulling it with the force, yes or no? Now, there's a common saying that I usually say that when there is a force, there must be an acceleration. Now, because of you have pulled this mass before, and this statement is proven using the second of motion. This states that the net force of the system is equals to the product of mass and acceleration. This is something I'll just write here. The net force, let me just write it here. The net force of the system is equals to the product of mass and acceleration, which is the idea of this system of motion. Now, compressing this mass with a force means that there will be automatic acceleration. And what do I mean? When this mass is at rest in your hand, when you compress it, if you leave this mass alone, it will want to come back to this equilibrium position with its maximum acceleration because you have applied the force. So when you compress something, you apply the force. And when you apply a force, acceleration is going to be there. And when acceleration is there, it's always going to be maximum. So during compression, acceleration is maximum because there's a force. And now remember that this mass is still in your hand. It's still at rest in your hand. Now the mass is the mass moving in your hand? The answer is no, because the mass is at rest in your hand. You are holding it in your hand. Now the energy value of an object position or at rest is known as potential energy. So it means that when the mass is in your hand, it is at rest, there will be maximum potential energy because the mass is at rest, it's not moving, it's in a particular position. So at this compression, the potential energy will be maximum because it is not moving. And the reason I'll come again, the reason why acceleration is maximum because the force is applied. Once there's a force, there will always be an acceleration, which is if that's the only thing you learn to be, you don't waste your time watching the video. Now, since the mass is at rest in your hand and it's not moving, it means that the kinetic energy is zero. Because kinetic energy is the energy of an object due to the motion. And since kinetic energy is zero, as Ke is zero, as zero because the object is at rest, it means that the mechanical energy of this system, we call mechanical energy is potential energy plus kinetic energy. And since kinetic energy is zero, it means that mechanical energy is just equals to potential energy. And the potential energy is maximum. It means that the mechanical energy of this compression is just equals to what? Maximum potential energy. That is for compression. So, in compression, the acceleration is maximum, the potential energy is maximum, the kinetic energy is zero, and then the mechanical energy is equals to maximum potential energy. Now, I will leave a equilibrium for you, the audience, to see what, or tell me what you feel it to be. Let's go on to expansion. Now, for expansion, now let's also work with it. Now, in expansion, use your hand to pull the string from the mass from its equilibrium position downward while still holding the mass. Now, while holding the mass, you use the force to pull it down. Like I said during the compression, once there's a force, there must be an acceleration. So it means that since you have pulled it down with the force, it means that the acceleration will be maximum because you pull it down, that is beyond the equilibrium position, with the force. And now since the mass is still at rest in your hand, it's not moving. And the energy value of an object position at rest is called potential energy. And that energy will be maximum because it's not moving. So it means that the potential energy will also be maximum. And since it's not moving, the earth is not moving in your hand, it means that the kinetic energy is zero because the energy value of an object motion is kinetic energy. And since the object is at rest, it's not in motion, the kinetic energy would be zero. So the kinetic energy, Ke, will be zero. And recall, mechanical energy is potential energy plus kinetic energy. So it means that the mechanical energy of expansion will be just equal to the mechanical energy, just equal to maximum potential energy. So the kinetic energy is zero. So I leave this to you. What do you think? What do you feel will happen to mechanical energy, potential energy, and kinetic energy as the equilibrium? Feel free to send your comments or answers in the comment section, and Let's see if you are close to the answer or not. So thank you for your time. Thank you for your patience. Thank you for being with me since the beginning of this video. I remain Mastermind or Mastermind Tutorial Limited. Have a